right, so welcome everyone to our next SIG SLT lecture. We're really excited to today have Jinming Zhao, who is a second-year PhD student at Monash University, with us. Her work and her talk today will focus on improving representations for spoken language translation, and we're really excited to hear more about this. For anyone who's watching the recording after the fact, feel free to reach out to her with any questions or feedback you might have. And for anyone who is interested in joining the talks in the future, potentially presenting, please join the SIG SLT Google group and get in touch with the lecture organizers who are linked there. So with that, I'm going to turn it over to her and we'll get going. So thanks so much.
Thanks, Elizabeth, for the introduction. Hello, everyone. I'm Jinming. Thanks for coming to my talk today. The title of my talk is Speech Translation, Effectiveness, Efficiency, and the Data. Here's the outline for my talk. Firstly, I will give you a brief background on speech translation. Next, I will introduce you my primary PhD work and present how we improve speech translation from the perspectives of effectiveness, efficiency, and the data. Let's kick off the presentation by introducing you the task. Speech translation is a task of translating an audio segment in one language to text in a foreign language. The conventional way of performing this task is the cascaded method, where people first train an ASR model. ASR stands for Automatic Speech Recognition. This model converts speech to text in the same language. Following to that, people train an MT model. MT stands for machine translation. This model translates the source sequence to the target sequence. Although this method has been popular for decades, it suffers from the problems of error propagation and high latency. So more recently, the end-to-end approach has become more popular, where practitioners use a single model to translate speech to text in one step. ST stands for speech translation. These models leave the problem of error propagation and have low latency. The major drawback, however, is that training these models require large-scale parallel data, which is not applicable for most language pairs. Now, with that background, let me introduce you our first work, titled Adaptor, Modality Adaptation for End-to-End Speech-to-Text Translation. Here is more background related to this work. One common remedy to address the data scarcity issue that I mentioned just now is by pre-training. Concretely, the idea is to pre-train an ASR system and an MT system with the available ASR data and MT data respectively. Then practitioners initialize a speech translation system with the pre-trained ASR encoder and the pre-trained text decoder. In fact, in the SODA architecture for translation, people use the Wave2Vet2 as the speech encoder and the MBOT decoder as the text decoder. Despite of promising empirical results, the major issue with this approach is that since the two modules are pre-trained on different modalities, when they are attached together, there is an inherent gap between them. And in this work, we name the gap as modality gap, which I will explain in the following slide. The cause of the modality gap lies in the fact that audio and the text are very different in nature. On the one hand, audio signals are much longer than the corresponding text sequence. Specifically, raw speech signals can be 1,000 times longer than the corresponding text sequence. Often, aggressive downsampling is deployed inside a speech encoder. But even so, the output of the encoder can still be 10 times longer than the corresponding textual counterparts. On the other hand, audio signals exhibit a much higher degree of variations, while text doesn't. When the content is given, for a certain piece of text, for example, V, its embedding is always the same. But for speech, V can be realized differently in consecutive vectors. Another variation aspect is that the number of speech vectors can also be different. To address the problem, we propose the Modality Adapter, short for Adaptor. This is a transformer-based architecture combined with convolutional layer. By design, it models both the global and the local dependencies of speech features while reducing the length of the sequence. It can be integrated easily with a pre-trained speech encoder and a pre-trained text decoder. In our work, we use the width to back to large as the encoder and the MBOT decoder as the text decoder because of their strong performance on speech translation in previous works. Now let's look at Adaptor more closely. The key to the architecture is multi-head put self-attention. I presume you're all familiar with self-attention. On the right-hand side, in the vanilla transformer layer on the right-hand side, the input and output sequences of this layer have the same length. By comparison, our multi-head put self-attention on the left-hand side is able to shrink the sequence. And this is achieved by having 3 pooling modules over QKV matrices respectively. And each pool module is a 1D convolutional layer. The degree of compression is controlled by the stride with this 1D convolutional layer. Following to that is the attention operations. By integrating convolutional operations into the self-attention mechanism, we essentially allow the model to learn both the global information as well as the local information while reducing the. But doing this is not enough. We also need to pull the input sequence in parallel to this block so that the sequence can be added on the top of this block. If we don't have this operation, there will be a length mismatch issue because of this addition operation. We conducted experiments over 3 language pairs from the MUSC benchmark, which is a dataset, which is a benchmark dataset in speech translation. We developed 2 variations of our systems. One has 1 adapter layer with a stride of 8 for the pool module. And the other one has 3 adapter layers with a stride of 2 for the pool module. Both of them compress the sequence by a ratio of 8. We compare our system with a range of baselines. Since our system uses a width to back to large and the MBOT decoder, for fair comparison, in one group of baselines, we use the same encoder and the same decoder and just replace our adapter with a CNN-based adapter or a transformer-based adapters. Notably, this was the SODA architecture while we were preparing for this work. Additionally, we also compare our systems with baselines that leverage additional data in the training process. Here are the results on the English to German pair. This refers to our training strategies. And these are the results for our systems, which are better than the baseline models under both training strategies. We also tested our approach on 2 more language pairs, and this table summarizes the results. Overall, our system outperformed the baseline model, which has the SODA architecture, by an average of 0.78 blue scores. We've also conducted an ablation study on Adaptor itself, and also additional analysis to evaluate the robustness of our system. Please refer to our paper for more details. In conclusion, we propose Adaptor, which is a novel transformer-based adapter to reduce the modality gap between speech and the text. Our system surpasses the strong baselines by a large margin. Having said that, the limitation is that Adaptor helps to improve translation quality at the expense of a high computation complexity. And this has strongly motivated our next work. Our next work is titled RedApt, an adapter for wave-to-vec2 encoding, faster and smaller speech translation without quality compromise. Here, the focus is to improve the efficiency of wave-to-vec2. Using pre-trained speech encoders often helps to boost translation quality significantly. But one bottleneck that we face in the previous work is that using these pre-trained speech encoders is very expensive. For example, with a 16 GB V100, we could only set batch size to 1. There are 2 reasons for the high cost. One is that raw audio signals are much longer than the corresponding text sequence. Second is that empirically, high-quality speech translation systems require much deeper encoders compared to text-to-text translation settings. So we are thinking, how can we make pre-trained speech encoders become more computationally efficient for speech translation? Our solution is to propose a lightweight adapter called reducer adapter, short for RedApt. The idea is to inject RedApt to pre-trained speech encoders, for example, wave-to-vec2. Showing in this figure, we can inject one RedApt layer after, for example, the first transformer layer. We could also inject this layer after the 10th transformer layer. And now this encoder has a hierarchical structure. The purpose is to reduce the length of a sequence while maintaining translation quality. Our RedApt is built on 2 CNN blocks. The first block is to compress a sequence by half. And the second block is designed to recapture local information. The intuition behind the second block is that certain information, for example, positional information, is lost during the pooling process. So it requires restoration. Our experimental results on 8 language pairs from the MASC-C benchmark show that both the efficiency of wave-to-vec2 and the translation quality improve significantly. And here are the results. This table shows the efficiency in various metrics. For throughput, the higher the better. For memory, the lower the better. And for flops, the lower the better. I would like to mention that the only difference between the baseline system and our system is that the baseline system has a CNN-based length adapter on the top of a width to back tool, whereas our system has integrated RedApt inside width to back tool. Both of the system compress the sequence by the same ratio. From the results, you can see that the efficiency of width to back tool and with our method has been reduced significantly. Not only that, but also to our positive surprise, the translation quality we even achieve better translation quality on most language pairs. Our hypothesis to this phenomenon is that reduction along the temporal dimension filters out redundancy and the noise from the spatial representations, which is beneficial to translation. We've also done various ablation studies. Firstly, we look at the impact of the number of RedApt layers, denoted as M. We set the values for M from 0 to 4. When M is set to 1, this is our baseline. It means that we use the vanilla width to back tool. When M is set to 4, it means that we inject 4 RedApt layers inside width to back tool. Overall, we observe a trade-off between translation quality and efficiency as the value of M increases. And then we decide to set the optimal value for M to 3 because it well balances the two factors. Now, given this, the next question is where inside width to back tool we should insert those RedApt layers. We've tried different configurations, and here are part of the results. This column refers to our position configurations. This is the baseline model, and these are our systems. Each row refers to one model, and each integer here indicates the position where we insert one RedApt layer. For example, when the number is 13, it means that we inject one RedApt layer after the 13th transformer layer of width to back tool. Although this is a hyperparameter, we didn't just choose them randomly. Initially, we segment transformer layers of width to back tool into different buckets. Then for each bucket, we try different configurations. Gradually, we shift our focus to the upper panel of width to back tool. Without going into the details of this table and explaining why the lower panel of width to back transformer layers didn't work, the key message from this table is that we choose 13, 15, 20 as our best configuration and apply it to other language pairs as in the results I showed you in the previous slide. We've also done analysis on RedApt itself. What we have found is that when we drop the second CNN block, the blue score drops by 0.44. And removing jello or layer norm would lead to convergence issues. Okay, so takeaway message from this work. We propose a RedApt, which is a lightweight adapter. It can be integrated with any pre-trained speech encoders. We conducted experiments with the width to back tool, but we expect that it will work for other pre-trained speech encoders as well. It helps to reduce the computation complexity while even improving translation quality. As our future work, we would like to use a neural architecture search to find the best positions. We would also like to extend RedApt to other speech processing tasks, because other tasks would also have similar problems. And this is all about this work. Now coming to our last work, where the focus is on data augmentation. It's titled Generating Synthetic Speech from SpokenVocab for Speech Translation. Just a recap, one major issue with end-to-end speech translation systems is that training them requires larger scale parallel data, which is not available for most language pairs. A practical solution to solve the data scarcity issue is to convert text-based machine translation data to speech translation data by TDS systems. However, using TDS systems can be tedious and slow. And this is the problem that we try to tackle in this work. We propose SpokenVocab as an alternative to TDS systems. SpokenVocab is a simple, efficient, and effective data augmentation technique. It can convert empty data to ST data on the fly. This figure illustrates how it works. There are two steps. The first step is to prepare SpokenVocab offline. How it works is that, given a word vocabulary, we use a TDS system to convert each item to audio and store it in the SpokenVocab. If the size of the word vocabulary is 1,000, this SpokenVocab we also have the size of 1,000. Meanwhile, we can configure the TDS system to generate different voices. So now in this SpokenVocab, there are 3 voices in total. In the second step, we convert empty data to ST data on the fly. So given an empty pair, this is the source sentence in English, and this is the target sentence in German. We first select one voice from the SpokenVocab bank, and then for each word in the source sentence, we retrieve the corresponding audio clip and then stitch them together. This is our synthetic speech. Pairing it with the corresponding translation sentence, we will then have a synthetic ST pair. During the training process, we mix real ST pairs with the synthetic ST pairs and then train systems with them together. Here's a demo for different, by the way, this stitch speech is disregarded afterwards. Here's a demo for different types of synthetic speech. And this is the stitch speech produced by SpokenVocab.
Thanks for listening to my talk.
Okay, and this is a synthetic speech produced by Google TDS API.
Thanks for listening to my talk.
Let me replay our synthetic speech one more time.
Thanks for listening to my talk.
You can hear that the sound is not natural, but you understand the content. In fact, for speech translation, our stitch speech works equally well as the TDS generated speech. Let me show you some results. I would like to quickly mention that in this work, we still use the MaskC dataset. And for our ST system, we use a width-to-vector large and MBOT decoder as the backbone. Okay. So in terms of our results, we first compare our stitch speech versus TDS generated speech. And here are the results. This row refers to the setting where we use a TDS system to convert MT data to ST data. And this row refers to the setting where we use SpokenVocab to do the conversion. And these are the results. You can see that our stitch speech works well just as the TDS generated speech. We're also interested to see how our stitch speech compared to real speech. So in another set of experiments, we use Europal. This is a realistic ST dataset. And this row refers to the setting where we use the original Europal dataset. So the speech is real. This row refers to the setting where we convert the transcripts of Europal to synthetic speech. And these are the results. It was quite surprising to us that our stitch speech even works better than real speech. We further investigate the impact of different designs of SpokenVocab. The first factor that we look at is how we prepare SpokenVocab and whether we add distortion to synthetic speech. We try different TDS systems with different sampling rates, and we've also tried adding different effects to synthetic speech. The conclusion is that using Google TDS system with 24 sampling rates and no distortion give us the best result. We've also looked at the impact of the number of voices. So we experimented with 1, 5, 10 voices. That is to say, we train 3 models and with the same amount of data and just vary the number of voices. It turns out that the 3 models have similar performance. So what it tells us is that Whistlebag2 is robust to different voices in this setting. Because of the flexibility that SpokenVocab provides, we also showcase how it can be applied to code switching speech translation to generate code switch speech. But given the time constraint, please refer to our paper for more details. In conclusion, we propose SpokenVocab, which is a simple, scalable, and effective data augmentation technique. In the context of speech translation, stitch speech works equally well as the TDS-generated speech. Since the SpokenVocab is a generic data augmentation technique, we expect that it can be extended to other content-driven speech processing tasks, for example, ASR. And this is all for this work. Lastly, I would like to thank my supervisors and the collaborators. I would also like to advertise myself a little bit. I'm currently looking for an internship for 2023. Please let me know if you have any openings. And below is my email address. You may also find my CV from this QR code. Thanks for your listening. Now I'm happy to take questions.
Thank you.
Thank you very much for a very interesting talk. And yeah, so I would encourage anyone who is watching the recording after the fact to please look at the email that was just posted and will be in the description of the video to reach out to Jinming about internships or also any questions you may have about the work or any of the additional details that might be in the paper if there are aspects that you are curious about that weren't gone into here. Yeah, thank you so much for a great talk. I am, yeah, I guess really interested to see some of the code switched experiments and I have a couple of questions on the first couple of sections as well. So I guess I'm going to use my temporary hosting powers to ask the first questions, though, feel free to join back in as well. So I think one first question I have about the reduction, it absolutely makes sense to increase the efficiency. And it's also very cool and sometimes surprising to see where the performance differences lie. I was wondering to what degree you looked at the correlation with, for example, the target sequence length. Like, did you pick 8 as the reduction rate to make a more one-to-one sequence length, or did you experiment with this a little bit? Yeah.
I presume you are talking about this table. You're referring to this table where I varied the value for M.
Mm-hmm. Yeah, so I guess I'm just wondering like what the different downsampling ratio means for the ratio for like the speech sequence length to the target sequence length, and if that was something that seems significant or perhaps not.
In our experiments, actually it is. So we set the cap on M to 4. The reason is that after 3, the length of the shrink sequence becomes smaller than the corresponding text sequence. And so, for example, when M is 4, the length becomes smaller. So our intuition is that when this is the case, potentially we will be losing a lot of information. And this is shown in this work. It was also shown in the first adapter work. I can quickly show you the one ablation study that we did for the first work. So here we vary the stride from 8 to 2. Here when we compress the sequence too much, the performance will also drop. Although I didn't include another stride, but we did one experiment by just increasing it a little bit further, and we observe a performance drop.
That makes a lot of sense. Thanks so much. And actually, I think my next question was going to be about low resource settings, so this slide might be perfect. I was wondering, so as you mentioned, and I think this is a really good observation, one of the reasons this might be helping is because it's reducing noise and therefore making it a little bit easier for the model to learn. So we might expect that this would be even more important with less data. And so, yeah, could you speak to any of the lower resource experiments you may have done, or what you might think would happen if you were to run those?
So in the Adaptor paper, we change the resource conditions from high to low. So this is the highest resource condition, and this is the lowest. So from this to this point, we can see that our system performs better than the baseline model. However, in the low resource condition, our system have the same performance with the baseline model. This was somehow expected because our model does require sufficiently larger training data. We would like to have a similar plot for our second work, which is the RedApt, but we haven't got the chance to do it yet. But in the future, I would like to run similar experiments.
That makes a lot of sense. Thanks so much. I think also like one aspect of this that seems very appealing is that it can be like an adapter added on to an existing pre-trained model. Of course, it's very difficult to train these models from scratch for many of us, but I wonder if you've looked at the impact of like when you incorporate it in the training sequence. So for example, if you've got a pre-trained model and you're adding these for fine-tuning or adaptation versus perhaps adding the adaptation during pre-training time. I don't know. I know I wouldn't be able to train this myself at home, so I'm not sure that you necessarily would have, but I'm just curious if you have any thoughts there.
So you mean we train a Wave2Vet tool with the injected adapters from scratch? Is that what you are
I
saying?
wonder, I imagine you haven't tried it, but do you have any intuitions about what might happen or any guesses? I'm personally.
I would actually be very interested to see that results as well. Because especially for speech translation, the content is very important. There are a lot of redundancy in speech speech signals that we don't actually need. That's why that's another motivation for our second work. And during the if we could do it during the pre-training process, that might even be more helpful, especially for those content-driven tasks, even for including ASR. But unfortunately, I don't have the resource available to me that I can do it.
This makes much sense. Yes, I'm in a similar boat. But yeah, it would be interesting to see. It's funny too, the disconnect, because like for pre-training, we're maybe not caring so much about the content, so we might not see a change in like the actual pre-trained model. But yeah, for ST. Yeah, so I guess I don't know if you've tried it, but have you tried to apply the same type of model, for example, to ASR or a task that is not translation, and so maybe there's less dependency on like a semantic unit, or maybe we need more or less of the local information, just out of curiosity.
Yeah, that's actually part of our future plan. We would like to extend RedApt to other speech processing tasks, because the computation complexity of pre-trained speech encoders is a common issue with a lot of speech processing tasks. And I just wanted to add one more comment on training from scratch. So. One future direction for our first work is that we would like to extend it to an entire encoder, so that it can have this gradual downsampling during the encoding process. And although we may not be able to train it from to train with a huge amount of data, but with the data available to us, for example, the MaskC dataset, it will be doable.
Yeah, that would be very interesting to see. Yeah, I wonder as well if like there might be a difference in which layers you can attach the RedApt adapter to, for example, if you're incorporating it earlier in training versus later. Maybe it's actually just taking it away from the like relationships it's learned early if you're fine-tuning with very different downsampling that I was seeing in pre-training. But yeah, it'd be very cool to see. I think my final question is to go to the third work, so something completely different. I think it's very cool to see that the stitched speech was potentially as beneficial as, for example, like the smoothed TTS. And yeah, it certainly could help for code switched speech. That would be very interesting to see, where it'd be easy to switch in different languages or voices. My question was about the number of speakers and when you experiment with different numbers of speakers. So here, when you're experimenting with different numbers of voices, are you, I'm guessing, taking each voice then has less training data, or is it the case that, for example, each voice has the same amount of training data and the training data is varied? So for example, like if you have 5 voices, is it the case that you have the same amount of data augmentation from TTS, or does it grow by 5x?
So in here, we train the model with the same amount of data. We
Okay.
didn't have the 5 times.
Yeah, no, that makes a lot of sense. So I guess part of the reason that I'm curious is I wonder at what point the threshold might drop off where you have too few examples per speaker, or at what point it might become less robust. I know, for example, in some of the past IWSLT tasks, for the low resource task, for example, some of the pre-trained data had enough speakers that they were wondering about this trade-off between how many speakers you need, how much data you need to see per speaker in pre-training in order for it to be able to generalize to new speakers. And so there might be a certain amount of data we need if we have a certain number of voices, like a relationship between data per voice and total training data. And I wonder, maybe spoken or like augmentation with synthesized voices would be a good place for us to control that, because it's so difficult to get enough labeled training data to run these types of ablation experiments. It would be interesting to see. But
Actually,
yeah.
in terms of voices,
Mhm.
my what I have found is that this is also what I mentioned just now when I was presenting this slide. So
Mhm.
the three systems that we train have similar performance, and
Mhm.
so what it tells us is that with VET2, just in terms of pre-trained encoders, it's robust to different voices in speech translation. Actually, after I got the results, I went to the literature and to see what others say about this phenomenon.
Mhm.
From one paper I read, it says that the speech in WIF2VET2 have actually, the representations of WIF2VET2 have removed speaker information. This is quite interesting to me. And I count and this is the one hypothesis that I have towards this table. So in this table, Europol has a lot more. It has a lot more speakers, but in our case, we only have one speaker, but we outperform the real speech. And I was suspecting that this might be the reason.
Yeah, that makes a lot of sense to me. I think I've seen somewhat conflicting things about how robust Wave2Vec2 is to speaker differences, but yeah, if you're kind of collapsing speaker variation with one synthetic voice, that would make a lot of sense if that were behind some of the improvements. Yeah, I'm excited to see more in the future for sure. And this was a very interesting talk, so thank you so much.
Great questions.
So I also have a a couple of questions in the last part. Now, at first, I had that thought about your spoken vocab approach seems like a kind of back translation in MT. Yeah. So in case of the back translation, we use some sampling based augmentation for the wider coverage of the possible inputs. So did you try to try to different sampling from the spoken vocab bank? Maybe you can more you can concatenate a very diverse signals, diverse spoken vocab. I think so. Did you try that kind of approach?
So you are suggesting a setting where instead of selecting one voice to generate the corresponding, I can use different voices to generate different words. So this is a setting. It's on my it's part of my future plan. Yeah, but thanks for the suggestion. It will be interesting to see that.
Okay, so the next question is about the difference in languages. So did you try another language? Typically in Japanese, intonations and the accent will be different in the context. So this kind of approach will not be effective in Japanese, I think. So I try to apply it to the other languages. So other than the what you conducting experiments at this time.
In terms of speech, currently we are only focusing on English as the source language, but it will be very interesting to see how it works for other languages, especially in speech. In that case, I will need to use a multilingual version of WIFTVAT to run the experiments. But it will be really interesting to see that, and maybe there's an opportunity for us to improve. To even improve SpokenVocab.
Okay, yeah. So in case of English, so it's really it's surprising to me to use the word level spoken vocabulary would help the speech translation, because also in English the intonation will change, somewhat change in the context, I think. But I'm wondering, so in case of Japanese, it's I think it's more difficult for the English case, I think, because of the drastic change of the accents in TTS. So actually the Japanese TTS researchers suffered from that kind of problem. So yeah, I really hope this kind of technology can be applied to the other languages, including Japanese.
Sure.
Yeah.
I presume in terms of the difficulty, in order to solve the difficulty that Japanese has, we can instead of producing spoken vocab on the word level, we can do it on n-gram levels. So that will help with the intonation and some other characteristics of Japanese.
Yeah,
that may help.
Great. Okay, my last question is about the application to the ASR. So this seems like the forward translation and data augmentation in machine translation. So usually it's not guaranteed to work effectively in machine translation. So what do you think about in the application to ASR?
I guess in that case, it depends on the language. If the source language is English, where the intonation may not matter that much as of what we can see from the results. But in terms of but if we apply spoken vocab to ASR when the source language is English, it should there's a high chance that it will work well. But in terms of Japanese as the source language, then there's still improvement for us to make, I guess.
How about Chinese?
Chinese, I'm not sure, unfortunately, although I'm from China.
Yeah. Okay, thank you very much. That's all from me.
Thanks for the questions.
Yeah, that's really interesting.
All right. Professor Nakamura, do you have any questions?
Yeah, but I had a question. It's a small question, but I have to leave this meeting. So I will ask Jinming directly. So actually, my question is really related to the RedApt, and if you insert the adapt layer into the wave to vec, but the original layer, for example, second transformer from the bottom. So this has this has the original time resolution, but you inserted the RedApt and try to reduce the temporal resolution. So, but still, the second transformer. So you use maybe I couldn't understand why you adjust this second transformer time resolution. while you are RedApt reduces the temporal resolution.
So this is actually, so your question is why I insert the RedApt after this layer? Is that your question?
No. Then no. This is not why. How?
How? Oh, so for instance, there are with VAT 2 large, there are 24 transformer layers. So optionally, we can select if we wanted to inject 3 RedApt layers inside those 24 layers, we can select different positions from them from 24 layers. So it can be in our best setting, we select one RedApt layer after the 13th layer, one after 15th, and one after the 20th.
Okay. So yeah, sorry about that, but so I should leave now. So so we will continue after the talk. So thank you very much anyway for your presentation. Thank you.
I'm also looking forward to questions from other people when they watch the recordings.
Yes, so just a reminder to anyone watching the recording, we will have her email in the description. Please do feel free to reach out and continue the conversation offline. I think with that, we might wrap up for the live session. Thank you again for a great talk and a really great discussion afterwards. So yeah, it was very great to have you.
Yeah, thank you very much.
Thanks, and thanks for the great questions.
Awesome.
See you next time.